Okay, so good morning. Thank you very much for inviting me. It's a real pleasure. It is great to be here in Obergurgl. I'm really impressed. So my feeling is it's not my last time here, although you never know at my age. But so I'll start with a few memories, forgotten memories from the early years. Basically, in '89, I moved from my native Bulgaria to England. So at that time, or approximately that time, I joined the Genesis project, which started with the Suprinum machine. So we had a Suprinum installation in Liverpool. That was Suprinum serial number 2. Parmax message passing, that was done by people like Rolf Hampel, a very nice colleague and friend. And later on, there was a problem with the Suprinum as a company. The European Commission was wondering what to do, and they said, okay, we are changing the industrial partner from Suprinum to Mako. And Mako, the Mako prototype, CS2 prototype, was the result of the Genesis project. We, of course, did the Genesis parallel benchmarks, which I was in a way, I was in charge of. We ran the benchmarks on the first Mako CS2 prototype, which was fantastic results. We never achieved better results than that one. Now, message passing was Parmax. The parallel benchmarks were very interesting effort because we introduced the hierarchical benchmarking performance analysis approach. Maybe not the first one, but that's what we wanted to do. Then we moved towards the portable parallel programming environments project. And that involved, you know, at that time there was things like PVM plus Parmax equals MPI, if you remember this effort. So there was the first MPI draft was something like 15 pages on paper. David Walker circulated this one, and I should have a copy somewhere at home, I guess. But MPI was fantastic. So that was a great effort. And it was successful, very successful. HPF was another great effort, and it wasn't as successful as MPI. But we did have HPF-like programming environments evaluation in the PPPE project. And at that time, we evaluated Vienna Fortran, for sure. Barbara Chapman was the key participant. There was a guy from Germany, Thomas Brandes, who had an HPF-like implementation, and we did quite a lot of interesting work with Thomas Brandes. And there was Levesque, what was his first name? John Levesque. So with John Levesque, he had a prototype HPF. So we did quite an interesting comparison. At that time, there was no Vampire. At that time, there was Paragraph, if some of you may or may not remember Paragraph. So that was the tool for monitoring visualization. Later on, having MPI, we of course did a new version of Genesis benchmarks using MPI because it was Parmax. We did PVM, we did MPI. We created, I mean, it was mainly Jack Dungarret, Tony Hay, and David Bailey getting together and saying, okay, let's create a park bench committee for parallel benchmarks, still following this hierarchical approach, which never worked, I'm sorry. We did try our best. Erich Strohmeyer was the guy putting together the versions of Parkbench in Knoxville, Tennessee. And at the same time, we got involved in the RAPS consortium, and that was real applications for parallel systems. And Carl Solchenbach was very influential, together again with Tony Hay and with, what was the name of the guy from ECMWF at that time, very actively.
Rolf Rattenseifer?
I'm sorry, but no, not Rolf, no. He was, anyway, but RAPS was not successful as a European project proposal. So the consortium decided it's okay, we'll just keep going, similar to, in a way, to APART. And it did continue with annual workshops in Reading. But basically what happened, the Genesis benchmarks became RAPS benchmarks at that time because Genesis had finished. Then from RAPS benchmark, they became Pallas benchmarks with Carl Solchenbach. When Pallas became part of Intel, they became Intel parallel benchmarks. And around early 2000, they were basically stable and fixed. And if you Google Intel parallel benchmarks, you'll probably see them somewhere. And then I go and see them, and I see my codes, and I'm kind of, yeah, great. They're still alive. Okay, so that's how, just in case we don't remember, this is paragraph 92. It is a collection of different windows, different screens that one can get from paragraph. Of course, message passing and animations. I don't know why paragraph was kind of discontinued and what was the reason to create Vampire. I think it was the changes in the system software, probably, and also the message passing environment again, but I'm still not sure. But I think there was a reason, and at that time, Vampire was developed. I remember Hans Christian Hoppe. Hans Christian, wait a minute. I'm not sure, but I remember Hans Christian Hoppe.
It was developed in Jülich by my former boss, Wolfgang Nagel. And then later it got sold to Intel, they bought it. But,
right. Well, I remember Hans Christian Hoppe giving presentations on Vampire. Yes. It's online. You can Google it. And I'm not claiming any authorship here. Yeah.
No, it was Pallas and Pallas, an architect.
Yeah, Pallas was definitely involved.
The measurement system. Because Vladimir only was a visualizer, and Pallas had the recording or something. So this is what they talked about. But the visualizer was from
But Pallas doesn't exist. There is no one who can claim anything at the moment. So it's all okay. But I'm just sharing my almost forgotten memories. And look, I found this great.
That was a name, but that's good that you have the slides there. Yeah.
In one of our PPPE technical reports submitted to the Commission, which are on my laptop, I found this great, you know. So
I also was in PPPE, it was my first project.
Here we go, yeah. So we're sharing, yeah, exactly.
This was my first EU project. It was a disaster. Do you remember that?
You know, another colleague from Southampton was in charge, and his name is David Pritchard, and unfortunately David Pritchard passed away, so I would imagine he would be able to talk more if he was alive. But anyway, So that's part of the memories.
Vladimir, you were with Manchester?
I was in Southampton.
You were in Southampton?
I was in Southampton. I moved to Southampton in '89. I spent 5 years in Southampton. Then I moved to Westminster in London. And that's something relatively new, recent, and more kind of future. So that's basically my abstract, the novel methodology. And it is part of community work. There's quite a lot of logos here. Probably the most important one is IRDS, International Roadmap for Devices and Systems. So I'll tell you a little bit about this and then about the benchmarking efforts in the international roadmap. Basically, the roadmap has long history, changing names over the years. It was a national initiative in the US, then it became international, then I don't know, something else happened. And then in 2016, the initiative became part of IEEE, so it became International Roadmap for Devices and Systems. It was renewed, restructured. The chair has always been the same guy, Paolo Gagliardi, who is used to be at Intel. It's a very active senior colleague from the community. What else should I tell you? It is related to the hardware industry. Now, being related to the hardware industry doesn't mean it is not the parallel performance or performance evaluation is not. It is actually very influential for them. They really want to see. So that's the structure of IRDS. Quite a lot of committees and teams. Some of them I don't really know the acronym of, but they're all here. The important thing is the system architecture team and the applications benchmarking team are supposed and have been working together, exchanging information and knowledge about the future development of the field. So anyway, it's all online. It is under irds.ieee.org or something like this. Yeah, it's here. So each of those teams is supposed to work on a specific or identify difficult challenges and basically stoppers of the development in that particular topic area, to prepare technology requirement guidelines and to exchange with the rest of the effort. So it's something like maybe 150 people involved in the whole thing, maybe more. The interaction between applications benchmarking and the system architecture is important, as I mentioned, because I'm in the applications benchmarking, as you can imagine, brings the critical understanding of what do we know and what will we need. I've got a misprint here. Came missing, to be able to compute in the future, and the system architecture guys work on the boundary conditions, space, weight, power, security, sustainability, edge, exascale. So 4 systems categories, I think they're mentioned later, so I'll just go ahead. From the applications benchmarking point of view, because of the rapid developments in the field, there is clearly need to identify the most important current and future application domains. In emerging applications that require new technologies so that they can be forwarded to the system architecture guys and then further down to the hardware teams. The hardware teams actually work very closely to the semiconductor industry and the hardware industry. So there's quite a number of members of those teams that come from companies. So these pictures are nice pictures of justification of AI and autonomy and augmented. So it's something but these are the four, what the system architecture colleagues call them, they call them market drivers. Cloud, Internet of Things and edge devices, cyber physical systems, and personal augmentation. So these are recognized currently, last year, as the market drivers. Next year, this may change, and things keep changing. But that's what it is at the moment.
So where does quantum computing fall into this class? Quantum computers, where do they fall? Is this not considered?
Right. So there is a specific new group, new team on quantum, and they are probably most likely going to be elevated to a full-size team and perhaps become part of the systems architecture. So there is some effort, but it is still kind of developing. I believe they have produced at least 1 or 2 white papers. So yes, it's not on this list. As long as the application areas are concerned, we have discussed recently one can identify a long list of applications areas. Now the question is, how do we rank them together with the system architectures people? Now there are traditional areas like discrete event simulation, even graphics, and these are currently being considered as not particularly important. What's important here? The key word important is to identify application areas that are going to affect the system architecture and the hardware design. So even if those application areas, say for example, discrete event simulation is a significant chunk of the community efforts, if it doesn't lead to application-specific requirements to the system architecture and the hardware, it may not be that important to follow. We know it's there, but it's covered, okay? So there's this risky decision that is usually done together with the system architecture people. And that's what I was just telling you about. The key application drivers may not be the full list of the application domains. But the mission is to identify those domains and the key application drivers and then try to come up with projections for the next long-term 15 years, short-term several years. I'm not sure whether you guys are, I'm sure you are aware that the life cycle of silicon industry is about 7 years. So talking to them, and we say, can you reduce this to like 6 or 5 years? They say no. Talking to Chinese colleagues, what is the life cycle of your silicon industry? They say 5 years. How did you? And they explain, they are, you know, very committed, working very hard. I was told, our engineers work very hard, Vladimir, which is true.
So when you say the life cycle, that means
from the beginning,
installing a new...
No, from the beginning in the research lab till the production line.
Okay, but it's not a semiconductor process going from 4 nanometers to 3 nanometers.
Oh, no, these are different, yeah. I just read an announcement, you may have read it as well, that a company in the Netherlands just installed equipment, a semiconductor company producing 7 nanometers. So this is the cross matrix, which is, you put Y, yes, almost everywhere, but these are the application areas and the market drivers. And then one can say, okay, let's see what is happening where. I have actually been mainly involved in the physical system simulation because this is where my background comes from. That's basically parallel and high performance computing, right?
So what is the difference there between machine learning for science and artificial intelligence? Because there is only one check mark, right, for the cloud, machine learning for science.
I'm not sure at the moment. I'm sorry, Michael, but there must be. We can get this offline.
Of the term there, right?
Right. So which are the critical issues? Changes in the software ecosystem impact application performance, and that's something that we already mentioned here. The software versions, and then things are different. Memory performance is one of the top critical issues. Power efficiency or energy consumption, very important. And the other thing is, it's for some application domains, it's very difficult to track quantitatively. So it's just not as simple as top 500. But these are known issues. Now, a few words about the, yeah, I'm okay with the time. I'll finish earlier because this is what we decided yesterday. So Moore's law. My understanding, I'm not claiming authorship here, but I think there is quite a lot of misunderstandings in the community. So Douglas Engelbart introduced scaling back in 1960. And it was a conference, and in the audience of this conference was a young engineer, Gordon Moore. And when Gordon listened to the scaling, that was the starting point for his estimate about the development pace of silicon technology. So before or when creating Intel as a company, he wanted to know how successful this is going to be, and he published this his famous paper with the, with the original sketch. And it's very important just to say, to mention again that what Gordon wrote in this paper is that the number of components that can be placed inexpensively on an integrated circuit doubles approximately every 2 years. So one thing is components, and the other key word is inexpensively. Now, because of the community excitement, because we are humans, right? So we are ready to be excited. So for whatever reason, we as a community, we started talking about Moore's law for clock cycle, which is not what he wrote about. So clock cycle was really following the same pattern in the 80s, in the 90s, and around 2000, or shortly after, this was no longer happening. So I don't have a similar curve for the time after that, because we know that this was no longer the case. So what was happening? 24 years ago, Intel predicted 10 gigahertz chips by 2011. 10 gigahertz. And that was published in ZDNet, and I probably keep a copy of this announcement. Has this prediction worked as before? Because this was based on 20, 30 years of history. No, it did not work. Later on, we were joking with Intel colleagues saying, you became now a software company, right? Because they were focusing mainly much more on compilers and software environment. So the interesting question is actually Moore's law going to end? And what are we going to do then? And many people give presentation and say, Moore's law is ending. We're going to do X, Y, Z. So is it ending? It's been ending for 20 years now. And it sounds scary. It can end tomorrow. What are we going to do then? The end is near. And what does it currently state? Because there has been all those modifications to the text. Now, there is a recent definition, and it says the number of people predicting the death of Moore's law doubles every 2 years. Who said this? This was Peter Lee, VP Microsoft Research in 2016. I'm not sure whether he's still VP in Microsoft. The number of VPs in Microsoft Research have gone. I don't know. But I like it. It's funny, and it is actually true. What's happening is the Dennard scaling stopped working 20 years ago. This is what happened, not Moore's law. And then we entered this new era of dark silicon. And this is when we started working with multi-threading and started addressing the energy consumption challenges. So Dennard scaling, that's Dennard's paper 74, which basically is quite an interesting one, because it says as the dimensions of a device go down, so does power consumption. So you scale down, and the power consumption goes down so that you can put more transistors on the same die, and the power consumption of this same die is more or less the same as before, but the number of transistors goes up and up. This is not true because of the leakage, which was negligible before, but approached the same order of magnitude as the chip's dynamic power, and that's it. It's physics. So this is the dark silicon era. It's not a big deal, because if you look at the thermal dynamic thermal diagram of a chip, even if it is not a thermal diagram, the chip never actually consumes high levels of energy across the whole area. It goes like this. It depends on the software, right? 1 core, 16 core, caches, whatever else. So what does that mean is that we can afford to have dark silicon, because even if half of the chip is not properly powered, it's still usually okay. So that's the dark silicon. Yeah, that's what I just mentioned. So the question is now, before we go to quickly to an example, the question is now, when do we need new architectures? From time to time, we basically build critical mass, and then the community says, new architecture. It is when we hit a wall for some important class of applications. So it is, so the first one in mid-90s, the memory wall, when I was very young, the clock cycle of Intel 8086 was the same as the clock cycle of the memory on the IBM PC. And this is 81, 82, around that time. So your memory access is basically as fast as your processing speed. Wonderful. But this was later not the case, and that was the first wall in mid-90s, the memory wall. And we're still struggling a lot with this. Of course, the solution was introduce cache memories, introduce memory hierarchies, I've been working with memory hierarchies myself, and I don't like it. But that's what it is. The power wall, which just mentioned, early 2000, 2004, then art scaling, emergence of dark silicon. That's it. Sorry, we are unable to use the whole of the die. Oops, sorry. And the third wall is approximately now the locality wall, as introduced by Peter Kogge. So Peter is also part of this effort. So the data locality we expect from our apps is disappearing. We are used to assuming that the data is local. Maybe not 100%. That's the basics of the memory hierarchy, right? And it is disappearing for whatever reason. New application domains, usually.
Is part of that because data spaces are getting so big, almost everything's a sparse representation now.
Yeah, exactly, yeah. And in particular, the new application domains, they are no longer nice, endless loops that keep accessing a small region of memory. But basically, I'm making here a risky statement, but Moore's law still works according to the IRDS roadmap. Why we can say this? Because the planning ahead, the silicon industry guys, they've got plans for 2035, for 2040, and they say, yeah, it's difficult, but we're going to make it. It's okay. We're going to do new constructions, three-dimensional, blah, 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 and it's going to work. Intel canceled the HPC uniprocessor projects around 20 years ago and moved to multi-threading and data level parallelism. And of course, modern processors, modern architectures, they are far beyond traditional microprocessors. It is the CPU, the GPU, FPGAs, ASICs. Note that we don't call this general purpose. General purpose is a very strange term that has never been properly defined. So it's flexibility. So flexible, the CPU or CPU-GPU combination are more flexible in terms of accommodating different application areas. But the efficiency is higher if you have an application-specific hardware like FPGAs, ASICs, and it keeps happening.
So where would you put the quantum chip or something like this? Is this between GPU and FPGA or something?
I don't know. It depends. I've got a little bit of knowledge. I joined one of those IEEE initiative on quantum benchmarking, and then we decided as a group that it is a little bit too early, so let's wait for a while and then we'll reactivate the quantum computing benchmarking a little bit later. It depends how the quantum computing is going to position itself in the computing systems landscape.
Can we ask Martin, if there would be a quantum chip, in your opinion, where would it be positioned?
It's
Depends when you do your observation.
Well, just...
Yeah. No, Thomas, yeah, we'll have to work on it, right?
The superposition of all these.
This is similar to my question yesterday when I asked Martin, how are you guys going to compile? So you've got a hybrid application and you have to compile it, and part of the executable will have to go to the quantum device and the other part going to whatever, GPU, CPU. How are you going to do this? It's an interesting, I'm sure a number of people are having a lot of fun working on that. So.
But it still would be interesting to
It's definitely further ahead because flexibility is lower. It's very specialized.
Yeah.
That's also a misconception because it's a traditional understanding of problem solving. We're looking at problems that we can solve with classical computing. That's our computer science mindset, right? And you're looking at suddenly a different class of problems. So that's also the future will see if maybe once you build it, they will come, right?
I still would guess it's between GPU and FPGA.
Well, here, even the quantum side, we have the spectrum. It's supposed to be general
Yeah.
purpose quantum, and it's supposed to be easy quantums with a specific application, even more specific one. But so you have the same spectrum of quantum too.
So what the quantum computing guys are maybe likely to do is they're maybe going to introduce another line and say, this is the traditional and this is the quantum. Maybe, I don't know. So we're struggling with those plateaus in application power versus performance. So that's the power consumption. And of course, specialization, I already mentioned, memory bandwidth. Are we going to solve the memory bandwidth problem? It's such a pain with those memory hierarchies, such a huge pain.
It's the damn speed of light.
And another thing, as IRDS is a big effort, but it is a volunteer effort. The fact that so many volunteers participate in IRDS is remarkable, both from academia, research institutions, and industry. But still, if you want to allocate a lot of cycles for something, they just don't have the approval of their management to do things for months. Maybe some sort of, I don't know, Paolo and Tom Conti may decide to, or manage to organize something with IEEE standardization.
Do you think it's really memory bandwidth or it's latency?
Yes. Oh, sorry. Yeah. It's both.
It's both, right?
Yeah.
And so these guys that predict the future, what do they say yet? So what will be the future there? Is it what we all think they are? There is a little bit and there is a bit and there, or is there something happening like PIMS or so? Have there any idea?
That's the system architectures if you're talking about PIMS.
Okay,
Yeah.
It's part of your roadmap.
When you look at like NVIDIA, where they're doing these incredible integrations of the CPU, GPU, and they're just putting an enormous amount of bandwidth between the components.
Yes.
Yeah.
So they're latency they can't fix, but they're
But
fine.
also photographs, right? Where you put significant memory on the wafer, right? So I could imagine that in the future we see more things like PIMS, right? So you read the processing and memory on the same chip, and then you simply keep going, right?
Well, you know, part of the machine learning accelerator market is going to message passing. So bring back your transputer, dust off your old transputer code.
OCAM.
What?
OCAM.
Yeah.
Yeah.
Yes.
Yeah. What you want, I mean, this is what we want. We want to see significant changes, big. And actually, it is all about small, incremental steps. Have we seen, I mean, we probably have seen revolutions like, I don't know, AI. Although when we were younger, AI was considered to be something like in the corner of computer science that we are not interested in. Right. Yeah, here is memory latency, bandwidth. And these are requirements for different application domains, at least the ones identified as important for the market drivers. Physical system simulations. This is now close to parallel benchmarking. So that's related to supercomputer, that's related to exascale. Of course, this is when we introduced the e-science term and area. Over the years, I mentioned this earlier, NAS parallel, Genesis, Park Bench, SPEC. these are all efforts trying to follow the benchmarking hierarchy approach, like micro benchmark, kernel, application. Maybe the last one I have seen, maybe you've seen more recent efforts, is the 7 dwarfs. Have you heard of the 7 dwarfs? That's in Berkeley. There used to be a technical report on the 7 dwarfs, and it is no longer online. But it is still mentioned. It is part of the Berkeley vision for parallel computing. They've got this famous paper report. The difficulty here is that you want to see 7 dwarfs, and then you say, okay, let's agree we've got 7. And then a little bit later, somebody comes and convincingly proves that you need 11. And then somebody else comes and says, wait a minute, we need 20-something. And then when this keeps happening, and then you say, it doesn't work. So current application domains are different from before. That's absolutely clear. I remember a submission to supercomputing was rejected because they were using NAS parallel benchmarks, and the reviewers didn't like the fact that in 2015, for example, that NAS parallel are out of date. So you want to evaluate, but of course this is personal view of the reviewers. The hierarchical benchmarking approach has been attractive, very attractive for many people, but it is practically not achievable. So that's what it is. Sorry. So what's possible? What we've done? We've selected, HPL. This is more easy to select, but HPCG sparse systems, and see if they cover the range across different performance results. HPL usually delivering the highest, and HPCG delivering the lowest performance, and see how wide is the gap. So these are not very recent, but still recent results. So the gap is not really nice. The gap is bad. And that's because of problems with memory latency. So approximately 2 orders of magnitude difference. This is what is this average performance across the recent 10 years. This is fraction of peak performance. So HPL is obviously close to 1, and HPCG is so low and depressing. Felix was mentioning, I'm sorry, Felix is not here now, but Felix was mentioning the other day, the application performance is only a few % of the peak. That's usual. People have been criticized. I remember in Los Alamos application, colleagues would be having very difficult time with the management, saying, we bought this brand new supercomputer and you're unable to deliver more than 5%. Fix your code. There is no way to fix the code. This is a little bit more about energy and floating point arithmetic. It's not actually on the graph, but it's mentioned here. So energy, monitoring energy and reducing power consumption is, of course, something that keeps happening, and it is an important aspect of the future development. And it is, everybody knows about it, so there is no need to convince system architecture and hardware developers that this is important. They know it. Higher bandwidth, lower latency for memory. HBM3, HBM4 probably, let's see what's going to happen later this year, next year. Maybe we are going to see some big changes in the memory systems. Floating point arithmetic, that's an interesting one. There is a floating point arithmetic standard, right? IEEE standard. And this one was supposed to expire in 2019. And at that time, I knew the chair of the standards committee, and I was several months earlier, and I was saying, John, are you guys going to do something about this? It expires in the summer. And he says, Vladimir, it doesn't work that way. If something happens, it will have to be initiated by the working group members. And if you look at the working group members, the standard floating point arithmetic, these are all big companies. So a little bit later, I spoke to IBM colleagues from Haifa, and they said, oh yeah, it's going to be just renewed. No changes. And this is what happened, no changes. So basically what's happening to the floating point arithmetic, the standard is there, and this is for backwards compatibility, important, so they don't want to change it for this reason. But in parallel, it's huge losses there, cycles, energy. In parallel, companies are going to introduce alternative decisions. Now, whether this is going to be standardized between the big companies, I'm not sure. I haven't heard of this. I know Jack Dongara and colleagues have been working on mixed precision codes so that you basically address the issue at the software code level. But there's so many applications. You can fix a few libraries or something. But another thing is to go for more radical approaches. Like there are more than one, but I mentioned here the POSIT arithmetic proposal that John Gustafson has been advocating about. It's a new solution of the floating point arithmetic. So that's basically what I wanted to tell you about. I think I have already mentioned those issues. The team members, these are the application benchmarking team members from different parts of the world, Japan being very active, and of course US, and not that many from Europe, so inviting colleagues to join from the European countries. And some external roadmap collaborations. This is the Embedded Microprocessor Benchmark Consortium. These are very interesting colleagues. They are part of the team. The Japanese, they've got their own system device roadmap committee. ML-PERF, machine learning performance, and also the National Institute of Standards and Technology. There are probably others. So this is not an exhaustive list. So thank you very much.